So now I'm going to look at the idea of rates. Okay, rates can also be, if you're dealing with something that might cause disease, you can also look at them as risk. Okay, what's the rate at which males recycle in this population? I'm going to go back to what I had before because these numbers are these differences are so small. If I can remember what it was, I'm going to make up a new one. Doesn't matter really. I'm going to say 20. Let's see, I have 60. Say 25 males recycle and 35 35 males don't recycle. That would leave 5 females down here and 35 females in here. Let's say that these are my observed values. This is what I actually calculated, the values that I observed. Okay, so now that's quite different than what you would expect, right? Before we had what we expected was 18 in here, we got 25. What we would have expected before in here was 12, we got 5. Quite different. So we know chi-square value is going to be pretty large if we actually worked it out for this. But let's take a look at this from another perspective. Okay, from the perspective of rate. What's the rate at which males recycle? What's the rate at which males recycle? Well, that's going to be equal to the rate at which males recycle is 25 out of 60. Right? Pretty simple. They recycle at the rate of 41%. 42% of males recycle. Well, what's the rate at which females recycle? Well, the rate at which females recycle is 5 out of 40 females that we sampled recycled. So that rate is going to be equal to 5 over 40. So they recycle at the rate of 12.5%. 42% of males recycle, 12.5% of females recycle. That's pretty interesting. Well, now I say to myself, it would really be handy to, instead of having to remember these two numbers, I calculate a relative rate, right? Which a relative rate or a relative risk. I'll talk about why I might use the term risk. I'm going to calculate something that gives me an idea of relatively how much more the males recycle than females recycle. Okay, and that's going to be equal to the rate that females recycle divided by the rate of males recycle the rate at which males recycle divided by the rate at which females recycle. And that's equal to 3.3. Males recycle at 3.3 times the rate that females recycle. Okay, well, that's pretty interesting, right? In other words, if you're a male, you're 3.3 times as likely as a female to recycle. Big difference, right? Well, I can look at this from other perspectives as well. Let's say that instead of male over here, we had exposure to asbestos, right? And this was no exposure to asbestos. And up on top here, we got, instead of recycle, we're looking at whether or not someone got lung cancer. Right? Well, now it's the same numbers, except now the rate that we're looking at is the rate of lung cancer among people that were exposed to asbestos versus the rate that people got lung cancer if they were not exposed to asbestos. So if these numbers were true, you'd be 3.3 times as likely to get lung cancer if you were exposed to asbestos. Okay, so now, that's very interesting. But instead of calling that rate, let's call that risk. So you could call RR, when you're talking about diseases, very often you refer to it as relative risk. In other words, the risk of getting lung cancer, if you're exposed to asbestos, is 25 out of 60 if you're a male, if you're exposed to asbestos, and 5 out of 40 if you're not exposed to asbestos. And then the relative risk is the first one divided by the second one. Make sense to you guys? Okay, so now that's a handy way to do this. Now let's say if I were to go back and look at my table, my expected values, right? These are the values that I would have expected if 30% of the males got recycle, and 30% of the females, I expect 18 males, 18 females. Let's calculate the relative risk or the rates for this population. That's going to be equal to, for our expected value, it's going to be equal to 18 out of 60, right? And for the males, 30% as we expected. And for the females, it's going to be equal to 12 out of 40. Oh, as we expected, they're both the same rate because that's why it's the expected values. Now, the relative risk or the relative rate is going to be equal to 0.3 divided by 0.3. It's going to be equal to 1. The risk of disease due to this exposure, the rate at which you're likely to be recycled if you're male or female. If there's no difference between the exposure, the exposed group and the unexposed group, the relative risk or the risk ratio is going to be equal to 1. Okay, so now when we did it here, it was not equal to 1, right? It's equal to 3.33. So would we reject the null? Let's say I start with a null hypothesis that the rate at which males recycle is equal to the rate at which females recycle. Okay, our alternative hypothesis is that they're not equal. If that null hypothesis is true, we would expect the relative risk or the rate to be equal to 1, right? Okay, it's equal to 3.33. Should I accept the null hypothesis or reject the null hypothesis that there's no difference in the rate between males and females? Anybody have an opinion about that? Okay, reject. Anybody else? Everybody agree to it? That's reject? Okay, reject sounds like a good idea. There's a little bit of an issue here, though. This is what we calculated for our sample, right? So our sample says that you're 3 times as likely to. I'm going to switch over to the idea of asbestos exposure. You're 3 times as likely to get lung cancer if you're exposed to asbestos. I'm inclined to think that that's probably true, that you can probably reject the null hypothesis. But when we're looking at this number, our problem is that that's the relative risk in our sample, in our observed values, not in the whole population of everyone exposed to asbestos and not exposed to asbestos. Okay, so in order to judge whether or not this number is really different than 1, right, what do I need to know? Instead of just the number itself, normally in a case like that where I want to compare this number to my expected rate, which is 1, what do I need to know in most cases? Okay, think back to what we usually use to compare a number to decide whether or not it was the same or different. An opinion? Right, what am I looking for? My confidence interval. Okay, this sample was 3.3. It's like when we take a mean. We know the mean is equal to the mean in sample is equal to a certain amount, but we want to know, well, what's the range that I can assume that the entire population mean is? Because I'm not interested in just a sample. I want to know about the population. That's why I did this study to begin with. So these 100 people suggest that it's 3.3, but what is the range of values that I can be sure that I can be 95% sure, less than 5% chance of being wrong, that I can say that this rate is really different than 1. Okay, well, my confidence interval will tell me that. Let's say my confidence interval is 2 to 4. Okay, in other words, it says it's 3.33, right? But it's really my 90 in this sample is 3.33, but my 95% confidence interval is 2 to 4. So I'm 95% sure the true risk, relative risk or risk ratio for exposure to asbestos is between 2 and 4, right? Can I reject the null hypothesis that the relative risk is equal to 1? Should I reject or fail to reject? Confidence interval is 2 to 4, right? We agree that it's going to reject, right? Now, if I had said that the confidence interval was, so I can't get in here to edit this, is 0.75, to 4. Do I accept or reject there? We fail to reject. Exactly right. Why do we fail to reject? Because we can't, since 1 is within this interval, we can't be 95% sure that it's not 1, right? Because the range that we're of 95% certainty is 0.75 to 4. So we can't say with 95% certainty that it's not 1. Now, when this was 2 and this was 4, we could say with 95% certainty it wasn't 1 because 1 wasn't within that interval of my 95% certainty. So if the calculated value for your risk ratio is outside of your confidence interval, you reject that null hypothesis. Okay, so now how do you calculate this 95% confidence interval? Well, if I go back here and I look at this, what was I working with here? I was working with a proportion. This proportion is equal to 25 over 60, right? 25 over 60. Okay, with a sample size of 60 males. Well, you guys remember that's a proportion. That's a p value, a p cap, right? That's a proportion for a sample, right? It's 0.1, and you have a sample size of 60. Well, you guys remember, if you have a proportion and you have the sample size, you have a way to calculate a confidence interval. Similarly, this is just a proportion. The 5 over 40 is a proportion and a sample size. You can calculate a standard error, and you can calculate a confidence interval. And actually, we're looking at the combination of these, 1 divided by the other. So we're going to get another proportion, and it's going to be a little complicated. So chances are you would only bother to do this using SPSS. But you can use these numbers, the same table, to calculate a confidence interval so that you can decide whether your result is statistically significant or not, whether or not you can reject or accept a null hypothesis. Now, I want to show you one other way of looking at this data, and that's called the odds ratio. Okay, so now, the way we looked at rate or risk, we looked at the number of people that got lung cancer divided by the total number of people in that group, number of males that got, number of asbestos exposed people out of 60 that got lung cancer, 25 out of 60. So we took 25 and divided by 60 and got a rate or risk of getting lung cancer if you were exposed to asbestos. Well, we're going to look at it a little bit differently. What are the odds of getting lung cancer if you're exposed to asbestos? Well, let's say, for instance, that this had been 25 and 25. Well, the odds would be 50-50, right? In other words, what we call 50 and 25 and 25, that's what we would call normally 50-50, half and half, right? Well, the odds are expressed that way. If one person got lung cancer and 10 didn't get lung cancer, we'd say your odds are 1 to 10. 1 to 10, right? Or 1/10 are your odds. That's different than your risk, which would be 1 over the total 11. So your odds are going to be 25 over 35, similar, but unlike our risk, which was 25 over 60. So our odds of getting lung cancer if we're exposed to asbestos are going to be equal to 25 divided by 35. Okay, so now our odds of getting lung cancer if we're not exposed to asbestos are going to be 5 divided by 35 instead of divided by 40. Okay, this is our odds of getting lung cancer if we're exposed to asbestos. This is odds of getting lung cancer if we're not exposed to asbestos. Now, I'm going to compare these two odds. I'm going to use something called the odds ratio. Anytime you hear ratio, it means that you're dividing one thing by another. So I'm going to divide the odds of getting lung cancer if you're male, if you're exposed, versus the odds if you're not exposed. And I get a number 5. You're 5 times as likely, right? That my odds are 5 times higher if I'm exposed to asbestos. Both of these are kind of similar numbers, but the math makes them come out a bit differently. What would I expect my odds ratio to be if there's no difference between being exposed and getting lung cancer, being exposed or not being exposed? Take a wild guess. What do you think this number would be if the null hypothesis is true and that there's no difference? What would we expect the odds to be? Quick opinion. right? What did I expect it to be before? I expected the odds ratio to be the same, the odds to be the same in both cases. So I would have expected it to be 1. Okay, is everybody comfortable with the idea that the ratio of the odds of being, if you were exposed to asbestos and get lung cancer, is over the odds if you're not exposed to being equal to 1? Same way we expected the relative risk to be equal to 1 if there's no difference. You guys okay with that? Can I get an opinion? Okay. Okay, good. Okay, so now what do I need to know here before I reject the null hypothesis? You have odds of 5 times, but I don't know if that's just because I had a small sample size, if by chance it really is 1, but in this particular group of 100 people I selected, it came out to be 5. What do I need to know in order to, since I'm only dealing with a sample, not the population, what do I need to know here again? In order to really evaluate whether I can reject the null hypothesis, I need to know the confidence interval again, right? And if I get a confidence interval, that's equal to, let's say my confidence interval is equal to 3.5 to 6.5. Do I accept or reject the null hypothesis? Okay, opinion, accept or reject the null hypothesis that there's no difference in the odds. Hang on a second. If the remember the odds ratio that we're comparing it to is 1, right? We want to make sure that 5 is really different than our expected, which would have been 1 if there's no difference. The confidence interval, if the confidence interval says it's 3.5 to 6.5, right? That means we're 95% sure the real odds ratio is 3.5 to 6.5. That means we're 95% sure that it's different than 1. Okay, so if 1 is not within that confidence interval, we reject the null hypothesis. If 1 is within this confidence interval, we fail to reject. In other words, here's a situation where you would fail to reject. Okay, let's say that this was 0.25 to 2.5. Right? 1 is within that confidence interval. I can't say with 95% certain that my confidence, my value is not 1, since it's within our confidence interval. So in this case, we fail to reject. If 1 is not in this interval, then we reject the null hypothesis. Okay? Make a note of that so you guys, remember how you use confidence interval. Okay, so the homework itself pretty much goes through a lot of this kind of stuff. Let me see if I can get back to it. Okay, let me zoom in here. So we can all see this. Okay, what's the first thing that's asked? Okay, now first thing is fill in the blanks. Okay, risk of illness if exposed. What's the risk of illness if exposed? Risk of illness if you're exposed is going to be A divided by A plus B, right? What I've done is set up a table here where instead of numbers, we represent it with letters. So you can kind of see where you go with the calculations. So this is these are the people that were ill. A number of people were exposed and became ill. C number of people were not exposed but became ill anyway, and that they were A plus C. Not ill is B and D. A total number exposed are A plus B, says this is our total here. Okay, risk of illness if you're not exposed. Well, C became ill, divided by C plus D. Odds of illness if you're exposed. That's going to be A divided by B. Odds of illness if not exposed. It's going to be C divided by D. So the risk ratio, right, is going to be A over A plus B divided by C over C plus D. Just the way you would do it. Good work, Jen. Yes. Just the way you would do it with if numbers were in these columns. The odds ratio is going to be equal to A over B divided by C over D, just the way you would do it if you were dealing with numbers. Excuse me. The overall prevalence of illness. What's the overall prevalence of the illness going to be? Somebody take a guess at what the overall prevalence of illness is going to be. Excellent. It's A plus C, the total number of people that got ill divided by the total number of people, right? Which is A plus C plus D. Very good. Critical value that chi-square must exceed to reject the null hypothesis. Well, we know this is a 2x2 table, which is 1 degree of freedom. So we can go to our chi-square table and we can look up what chi-square value we have to exceed to reject the null hypothesis. We already know what that is. We just used that number a short while ago, that 3.84. Okay, next part. Okay, we have a contingency table that we ask you to draw. Okay, and basically, you're going to go back here and you're going to say, oh, how many people got, 100 people got ill. You surveyed 100 people, so that's your total. Out of 100 people, 63 ate the tuna surprise, right? And that leaves 37 people who didn't eat it. Out of the 100 who did not report symptoms, 24 ate the tuna surprise. So 24 people out of the ones that didn't eat it. Let me see, 100 people were affected. We surveyed 200 people. So, yeah, we started you off with 100 and 100 and 200. So you know how many people ate. They tell you in the narrative how many people ate the tuna surprise, how many people skipped the tuna surprise, what the total number of people was, what the total number of people was here, total number of people here, how many got ill that ate the tuna surprise, so on and so forth. So you can fill in these boxes based on reading. Did I put the totals in wrong? Totals were in the wrong place on the graph. You mean in here? Jen, where do you mean? You mean on the example I was just working on, or you mean this one? 100 and 100. Let's see. What did the example say? Following a turn, you were able to 100 people who were affected. Oh, you're right. 100 people were affected, and 100 people who became, let's see, out of 100 people were affected, and 100 people did not become ill. You're right. The totals should be, the 100 should be down here and down here. I'm going to redo that. I'll put a new version of this up, or you can just change it yourself, right? It's a Word document. You should be able to change it. So the layout of the table is going to be a little bit different than the way I described it. The number of people that ate the tuna salad surprise, let's see, out of 100 people became ill, 63 people ate the tuna surprise. So 100 people became ill, 63 people ate the tuna surprise, right? That leaves 27 people who didn't eat the, 27 people, 37 people who did not eat the tuna surprise. Okay, that means that if we got 100 people, let's see, not ill was 100 people also. And let's see, 100 people ate the tuna surprise. Of the 100 who did not report symptoms, 24, of the 100 did not report, 24 ate the tuna surprise. Okay, of the 100, out of 100 people that didn't eat it, you had 24 people, right? So this is going to be equal to 76, right? So this is going to be equal to, we had 90, let's see, 90, 87, and over here we got, well, let me highlight this, and over here we got 113, okay, for 200 people total. Okay, so now, if there's no difference between eating the tuna surprise, what was the prevalence of illness in this sample? Well, we had 100 people that became ill out of 200 people. So we would expect half of those people, half of the people out of our total got ill. So if we have 87 people who got ill that ate the tuna surprise, 87 people that ate the tuna surprise, we would expect half of them, just as here, 100 out of 200 out of totals, we would expect half of those 87 to get ill. So we would have expected, instead of 63, we would have expected in here, we would have expected half of 87, which is going to be 43.5. Okay, that would have been our expected values. For 113, we would have expected half to be sick. So here, we would have expected half of 113 is going to be 56.5. And so on and so forth. You continue. Then you can just subtract this from 87 to get the number not ill, and so on and so forth. So you're going to have your observed values, which is going to be 63, 37, 24, 76. And then you're going to have your expected values, 43, 50, your expected values, 43, 56, so on and so forth. Okay, and then you can use those numbers to calculate your chi-square, your odds ratio, and whatever else that we ask of you there. Now, in this one gets a little more complicated. For starters, it's no longer a 2x2 table. This is a 2x3 table. So we're working with 2 degrees of freedom instead of 1 degree of freedom. Okay, 3 minus 1 is 2, times 2 minus 1 is 1, 2 times 1 is 2, 2 degrees of freedom. Okay, so in this case, we found that we looked at the physician's specialty, and we looked to see whether they recommended surgery. They took a conservative approach, likely take somewhat conservative surgical recommendation. If they were conservative, they recommended surgery. They recommended a conservative approach with surgery, or took a conservative approach regardless of the age of the patient, and so on and so forth. Right? Well, let's see what overall, that if we add up the totals here, what we would have expected to occur. Okay, so let's see. Among internists, let's see, we got a total of, we got a total of 28 recommendations for surgery. 29. We got, let's see, 83. We've got 42, 169. So we have a total number of internists and surgeons that we sampled. Let me get my calculator here. Total number of surgeons that we sampled was, let's see, 29 plus 83 plus 169. So we sampled a total of, lost it there, 281 physicians. Okay, of those 281 physicians, 29 out of 281 recommended a conservative, recommended surgery, radical surgery. 29 out of 281. So that percentage, let's see what that percentage is. That percentage, 29 divided by 281 equals, that's about 10%. So if I look at this, how many internists did we have here? We had 42 and 22, which is 64, and 6 is 70 internists. And we had, that difference here has to be 211, I guess, right? 211 surgeons. So let's take a look at this. If we had 70 surgeons, 70 internists, right? The percentage overall that all of the doctors recommended radical surgery was 29 over 281, or about 10%, right? So if I look at just the internists, right? Well, I would expect that out of 70 internists, 10% of them, same percentage as 29 out of 281, would recommend radical surgery. Or in other words, roughly 7 would recommend radical surgery. Well, what about how many of them would recommend conservative surgery, right? Which is going to be next column. Well, overall, it was 83. So this came out to be, what percentage was this again? This percentage was, oh, my calculator's gone again. Okay, this percentage was, let's see, 29 divided by, divided by 281. This percentage was 10.2. Okay. This percentage, 83 out of 281. Is equal to about 29.5. And this percentage is going to be what's going to be this and this subtracted from 100%, but I'm going to just do it on here because it'll be quicker. It'll be 169 divided by 281 equals about 60%, 60.1%. Okay, added together, these should add up, forgetting about rounding errors, are going to add up to 100%. Okay, we would expect 10% of the surgeons to recommend radical surgery if there's no difference between internists and surgeons. Okay, these are observed values that are in this box, the actual recommendations of the surgeons and internists. Okay, so now, what about this one, a conservative? We would expect 30% of these 29.5 or 30%, you can do it a little bit more accurately when you try it at home. We would expect 30% of our doctors, based on the totals, 30%, to recommend the conservative surgical approach, CR. Well, 70 among the internists, we got 30% of 70 is 21. So we got more than a little bit more than we expected. And we expect 60%, about 42, to recommend a conservative approach. Well, it worked out pretty good. Well, now how about with the surgeons? Well, again, we'd expect 10% of these guys, right? About 21, right? Instead of the 23 that we got, we'd expect 30% of the 211, or roughly 60, 30% be 0.3 times 21 be 60, let's say 60, well, let's see, this is going to be, see, 60% of this is going to be 120, say 120. Okay, when you actually do the numbers here, when you actually figure out the actual numbers, 30% of 211 is going to be 30%, 3, it's going to be about 60. Okay, when you actually do the numbers, you'll see that there's a difference between surgeons tend to recommend radical surgery more than you would have expected overall. Internists recommend radical surgery less than you would have expected overall. Okay, so now your task is to figure out whether or not your observed values, 6, 23, 22, 61, 22, 127, are different enough from your expected values, the ones in parentheses. And remember, these are just estimates. If they're different enough for you to reject the null hypothesis that there's no difference in the rate at which internists and surgeons recommend radical surgical techniques. Okay, so it's your task to figure out whether or not you can use chi-square, whether or not chi-square gives you the evidence that you need to reject that null hypothesis. Okay, what I'm going to do is I'm going to leave this up to you to go ahead and give a try. And afterwards, what I'll do is in a day or two, I'll put up another video where I actually work out the solution to this. Okay, so that like you can then work through it, like with me, and see if you got the same answer that I did. This is a little bit more complicated than these previous 2x2 samples that we got. So you should be able to do both these 2x2 ones on your own. I'll give you a little bit of a nudge in a day or two on this last one, so that if you're having difficulty with a little bit of the math,